Last time, we introduced linear classification as added an appendix to a feature extraction. Today, we will build in the deep neural networks as a feature extractor. Where in a way we are going to be opening up the back box that we introduced last time. So last time we said the raw data representation comes in. It's not necessarily ready to be separated in the linear space with a linear model. So we just made up a feature extractor, f of x, that's not necessarily trainable, that reflects our data uh, as an embedding. So that's a word that we use uh, pretty much in AI these days. And embedding has a deeper meaning. I'll get to that later on. But in this set of embedding is a representation of the input data such that it does the job that we would like. And the job that we would like for it to accomplish is being able to be separated within classes using only a linear model. So that's its job. And therefore, this is the embedding. But embedding, strictly speaking, can refer to different things for different desires. That's a topic for future. But how we concluded last week was if we assume that there is a feature extractor that takes our data as input to a linear model, we could learn this linear model through stochastic gradient descent, and that's what we covered. We actually, if you remember from basic machine learning classes, we actually saw something like a feature extractor that can convert an otherwise non-linearly separable space into a linearly separable um, setup as, for example, kernel functions in models like support vector machines or kernel plus a logistic regression. So for example, look at this data set. We collect two measurements for from a cohort. This is a very famous, presented, non-linearly separable but easily approachable problem when the kernel machines are being introduced. So let's assume that we collect x1 and x2. Let's say these x1 and x2 are some biomarkers to decide cancer versus benign of a tissue. And we obtain our metrics, and we get our data set as such. So obviously, logistic regression or linear models are not going to work for that. But again, this is previously introduced for kernel machines. But keep on with me. I'm going to build on top of this to introduce the functionality of neural networks in the raw data representation. So this is something very similar to what I draw previously, a function extractor plus followed by a linear model. Feature extractor, which is a trainable, non-trainable function that's a deterministic function, followed by a linear model. As in the entrance, as the beginning, we get our raw representation that's not linearly separable, and our input dimensionality is typically referred to as x for the sake of simplicity. And since we can monitor only 2 to 3 dimensional data representations, x1 and x2, right? And this kernel machine, obviously, since what we presented was something circular, a smart kernel machine, which is represented with the Greek letter capital Phi, is getting its radius and theta, the angle, right? So we can apply these two functions, square root of x1 squared plus x2 squared. It does something from whatever we collect and then gets another thing. And theta, similarly, arctangent of x2 divided by x1 gets the phi, gets the theta, gets the angle. And there, uh, when we convert our data, we get a linearly separable space, our theta space, right? And from here, our linear model can learn using stochastic gradient descent, as we covered last time. So in another way to demonstrate how it functions in this very example, the input to our classifier, which is a concatenation of the capital Phi, the kernel machine, and the linear model, is not necessarily linearly separable, but the kernel machine takes the x1, x2 space into our theta space, and see how it changes, how it wraps up the red samples, the cancer samples from blue healthy samples. And from the R point of view, obviously the radius from the origin of the cancer samples are small, and the theta changes similarly. We actually do not need the theta dimension at all, and the linear model does its magic to separate. So that's all good, and that's one famous example that's typically given when introducing the kernel machines. And as you notice at the linear model, the word linear has line in it, and linear model, the job of linear model is to draw lines, right? So it draws this line that separates the red from the blue samples. So very briefly, what we are achieving with feature extraction is in order to solve a nonlinear problem, which is difficult to approach, we split the problem into two. One, instead of drawing a nonlinear curve or drawing a nonlinear uh, uh, decision boundary, we warp the space. We calculate some other representation in the new space, and which is a nonlinear representation. And in the ultimate space, we solve the nonlinear problem. So let's keep on thinking about how this problem evolves, what we are talking about, in a slightly more difficult situation in which, again, we collect what we can. The X1 and X2 is our physical world, something that we can collect, something that the data presents us in a measurable dimension. But the task of separating red versus blue is not necessarily perfectly coherent with what we collect. So that's the main problem of data collection and data science. And we just wish that the red versus blue samples can be separated linearly um, from what we could collect. Obviously, this doesn't work, and we mentioned that we could try to find a kernel machine that's going to do its magic as it did a moment ago, so that red versus blue can be linearly separable. So we just wish if there was a kernel machine that could transfer our x1 and x2 axes into some other axis that's between a1 and a2. And if I look at the data from the perspective of a1 and a2, which is nonlinear from my original observation, but very functional in that space in terms of linear separability. This and here on the right hand side, you see when we are looking from A1 and A2 perspective, um, red versus blue is very easily separable. Then the problem is like one problem, how am I going to draw that or engineer that? But before I move on to this, I would like you to see this almost looks like something very familiar, except a little bit nonlinear. If you think that this looks something familiar, changing of the space, that looks like something like the PCA. And yes, PCA is a linear manifold learning. So right now, what we are learning here, what we are designing here, A1 versus A2, the better way to look at the data in the new axes is a principal component analysis kind of approach. But in here, the A1 and A2 is a nonlinear manifold. So the best linear manifold is approached with principal component analysis. But right now we are building on top of it. And here comes the question. How do we design the phi function that's going to give me the A1 and A2, like the unwrap the matrix, unwrap the space as I wish. The previous example was just so nice, neat, and it was able to like get the R and theta that enabled me to classify linearly. But the problem looks a little bit more more difficult here because you know what, we don't necessarily see the data see the data as humans in this nice two-dimensional world. Your data is most often than not more dimensional, say thousands of dimensional. So we do not have the capability to visualize it as such always, and to understand, to design, so to say, what the phi function should be. So I'm going to delete the word design and I'm going to make it learn, right? So we would like to learn the phi, the kernel function that is going to warp in such a way that my data set is then linearly separable. So that's our goal, learning to warp the space such that at the end of the things, it is linearly separable, which brings us deep neural network, which is the topic of today's video. So the deep neural networks is a function just like the linear. Remember, these neurons, these connections are nothing but inner products, as I introduced in the linear layer, linear classification layer. And these inner products are conducted via matrix multiplication, interleaved with nonlinearities. There is a very good reason that deep neural networks are composed of matrix multiplications, because matrix multiplication operation is very efficiently conducted with the hardware that we have, meaning GPUs. The moment that you read the data from the memory, which is the expensive thing, do as much operation as you can, such that your output in terms of floating point operations per second is maximized. So the deep neural networks, mostly the meaty chunk, everything about deep neural networks, even in transformers, convolutional neural networks, recurrent neural networks, any kind of deep neural network, um, they use matrix multiplications as the primary operation. Um, the data that flows to these matrix multiplications are different in different schemes, and we will be seeing them in our following weeks when we process text data, when we process sequential data, when we process image data, when we process video, when we process structured data. They will all take different forms, different inputs, but the long story short, it's almost always the same. Matrix multiplication, some nonlinearity, and some other things that we will reveal later on. So the story then becomes something like the input is when we had the top form, like the input is gone through this black box feature extractor. We did not worry about it last time. And the linear classification layer gives us the logits or the probabilities that does what we want it to do. Two, now we're opening up this black box. And this black box, as our first neural network, is nothing but the same box, non-linear, linear, 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 several linear layers interleaved with nonlinearities. And in a minute, I will go ahead and um, explain what happens under the hood of these nonlinear, linear plus nonlinear um, layers, and how they are trained, and how it actually does and learns the necessary function that um, gets you the embedding that the linear classification is done. But before I move on to this, I would like to mention that you see this blue vector I put here necessarily such that the story is complete. When the deep neural networks are introduced, these blue vectors are not necessarily represented. Like, people don't pause there and understand, oh, that's the space at which I am linearly separable. It's deep neural networks are typically introduced as concatenation of linear, nonlinear, linear layers interleaved with nonlinear activations. And therefore, you can see linear, 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 and another linear, right? The only difference is that the top layer has a different nonlinearity. That's something that we covered actually, which is softmax nonlinearity for multi-class classification. All right, now let's go ahead and introduce deep neural networks from the architecture perspective as it does the function of feature extraction in machine learning. So we've mentioned previously that the deep neural networks takes as input our vectors, right? So that's, let's say, my x, and I will be drawing our inputs just like column vectors. And all of our inputs are going to be represented as column vectors, whether it is an image, a patch of an image, is a window of a sequence, or a sample in a structured input, yada yada yada. Everything is going to be something like this, which will then be formed into batches of them. But that's a different issue. And so we represent x as in r to the d, like d-dimensional vector, right? And the most famous depiction of neural networks, you see actual nets, right? Like this um, elements, every index of a vector, input vector is tied and creates a neuron. And this, we know this neuron is summation of all over 1 to d. It is weighted with some indices, and it's the WIXI gives you your neuron activation plus some bias, right? Similarly, you can get several other representations, and which gives you another inner product, yada yada yada. So you already see a little web of a network is being created. That's just one layer. That's all fancy to look at, but I'm going to go ahead and delete this. I'm going to write it in a more represented in a more mathematically manageable form, which is inner product. You saw this summation, right? And you see the summation with all of the weights is nothing but an inner product between two vectors. So one vector, I'm going to take the color baby blue for trainable parameters. um, One vector can give you inner product with one vector. I'm going to write it as a raw vector such that I'm going to call it W, and the output can then become W transpose X. You see that this is a neat representation from linear algebra, and it's defined as this equivalent triangle is means that it's I equal 1 to D Xi Wi. So this represents the inner product. That's neat. And we calculate a bunch of them. So we will have a bunch of these row vectors, and therefore a bunch of row vectors stacked on top of each other create a matrix. So I'm going to draw a matrix here. This matrix is my first layer of my neural network. And you see in this matrix, I'm going to highlight every single row, because rows of this matrix are important. There will be W1, the first row, and W2, the second row. Actually, let me not write W2 so close to the W, because I will add one more thing here. And I have my third row, W3, and I have several of them. And the outputs of each and every one of these rows, as you see, are going to be W1 transpose X, W2 transpose X, W3 transpose X, yada, yada, yada. Now you have an understanding of what one layer of a neural network is. It's just a matrix. And what the shape of this layer is, you know the number of columns have to match the input shape, and the number of rows dictate the number of outputs in an layer. So that's great. And that was the case in my linear classifier too. That's nothing new. But that's going to be my only my first layer. So I'm going to call this guy my W1. That's going to be my W1. And therefore all of these row vectors, which I'm not going to call them W1 because I just defined my column vectors to be like this. So like X, Y, they by convention they are described as column vectors. So I'm going to represent my row vectors with transpose, so such that they are known, they are row vectors. And since this is W1, there will be other W's here as I will draw. These row vectors, the first row of first layer is going to be W11, and this is going to be W12, W13, and so on and so forth, Right. So that's my first output, except I can still add one more thing, the bias. If you remember, that we said an output y can be summation of I equals 1 to d wi xi plus some b. And I would like to add this b, but this addition, I would like to make this addition just like just like in linear algebra 2. So what I'm going to do, I'm going to append, let me take another color, the purple, to append the input vector with just 1. And I place next to it this B1. And you see the first column, first row, like inner product of this input, and the first row is going to be W1 transpose X plus B, right? So therefore, I will just have my bias vector right next to here too. There's B1, B2, B3, yada, yada, yada. And that's going to be my B1. Therefore, this is going to be my B11, B12, B13, and so on and so forth. At this point, let me delete this too. At this point, you have an understanding again what the shape of the bias vector is. Bias vector is a vector. Bias of a layer is a vector with the same number of dimensions as the output, not the input. So the matrix is output times input shape, and the bias is number of outputs, output neurons. So that's your um, layer. And this layer is going to have an activation. So notice how I am drawing my trainable parameters as with baby blue color. And these are going to be my activations. I'm going to call this activation H1, the first hidden layer activation, H for hidden. And I am supposed to draw another layer and another layer and another layer, but wait a second. I know if I draw another layer, which is going to be W2 and W3, yada, 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 and if I concatenate W1, so H1 equals to W1x, and if I make H2 equals W2 H1, then H2 becomes W2 W1x, which is it's just a matmul, it becomes another W. So that would make it, even though I'm concatenating all bunch of trainable parameters, I'm not contributing so much to the complexity of the function. I'm not getting something nonlinear out of linear. Therefore, I need to add something between layers, which is nonlinearity. For the nonlinearity is an element-wise function. I'm going to draw this function like a circle here. I'm going to write a little bit S-like sigmoid shape because the sigmoid function is one of the first nonlinearity functions that we saw that we that was introduced. And therefore, I will have an activation whose elements, this A11 is going to be some sigma times H11. And similarly, this guy will be A12 is going to be some sigma times, not times, sigma of H12, and so on and so forth. And I'm going to call this vector A1. Um, Notice how I am not actually labeling every single weight element that composes the next layer, and I'm not trying to write every single element of the hidden layer activations and hidden layer outputs and the activations. Instead, I am trying to represent everything in as much as possible vectors and matrices because you will see in a second that when we do it as such, um, the calculations will be significantly simpler. All right, so that was my layer number one. Layer number two is similarly another matrix, and this matrix will have as many rows as I want its neuron activations to be. And similarly, I will append this one with 1, 2. Therefore, I will, if I want, have a different set of biases. So I will call this W2, and this will be my B2. And I will similarly have my output with different color, and that's going to be my H2. Now I'm getting some nonlinearity, and hopefully I made a different function kernel from what I had in X. They got mixed and matched. They got smooshed. Hopefully, these nonlinearities are going to introduce some functions that are going to be useful for making my otherwise nonlinearly separable space. This is going to be my A2. And now my A2, hopefully, I can call this, I'm going to stop here, but otherwise I can go all the way to, I don't know, hundreds of deep neural networks. I'm going to call my, not A, I'm going to call my embedding that's going to be useful for me to linearly separate. And now I'm drawing my classification layer. Let's say my classification layer, I have my three classes, right? Cats, dogs, and elephants. So this is going to call for a classification um, layer W3. Notice I have W31 transpose, W32 transpose, W33 transpose. I have three rows because I would like to have three logits, right? And very similarly, I could append this one and have its biases uh, as a part of the trainable network here, B3. And at this part, we have something familiar from last week. We have our Z, and remember what we called it, logits, right? And from this logits, what I implement, let me get another color. We would like to get the probability, right? So I'm going to call it softmax function. The softmax function, it gives me from X to Y. And notice I am always representing vectors as z, y, etc. But each and every one of these terms, so say my y1 is defined as triangle over equal is defined as, pronounced defined as, is probability of c1 given x. So that's what it is giving me, all the way from x to probability, right? And using this, what I will have is I will use, in order to train, I will use my real labels, and I will use a cross entropy cost function, and I will get my loss at the end. So that's our first architecture of a neural network. This looks nice with all of these boxes and graphics and etc. But now it is time to convert this into a mathematical form. That said, I would like to start by saying that a neural network has three phases. So the first phase is what we want it to be. It's a function. It's a mathematical function that is going to do the kernel operation, if you will, in the very example that we introduced. Um, so the first is the forwards. So in the forward mode, it is, as I mentioned, it is one job. It takes X and gives you Y, and everything along the way. So in the forward function, um, in the forward mode, the forward understanding, forward phase, a DNN, a neural network, a, actually I would say a neural net is a mathematical function, which is my phi that takes X as input and gives, I should say, gives and yields the output as well as all intermediate activations. So this last part, this is quite important because the moment that you train a neural network to give you something at the very output, you can always use intermediate activations. Everything that you see in color black, you can actually use it for some of your usages. Say you would like to you have trained a neural network that classifies between different animals or different topics starting from a text, and then you want to use this neural network that was trained in a way to for classification um, to function as a feature extractor that will take any text that you provide and then gives you a vector. So what you can do, you can input your text. Your text is going to be represented as input vectors, which we'll call tokens in advanced courses like NLP, and then gives you some embedding, either A2 or H2 or the one that's before the classification layer is typically called the embedding. So that's our forward mode. Uh, in the forward, actually, let me do the three phases, and now we can continue what the forward mode as a function doing. And since we have described forward, there's a backward. So in the backward mode, we calculate the derivative um, of every weight with respect to the output, right? The derivative of every trainable parameter in a neural net with respect to the loss L is calculated via error backpropagation. All right. And finally, why did I calculate this? I calculated the dl over dw, and that's going to be my step direction. That's going to be my delta. And lastly, I will use that to update my neural network. The update happens with using the derivatives. The model is updated using the derivatives calculated in the backward phase. So typically what we do is we use something that we introduced last week, SGD, or some momentum-esque methodology like ADAM, Ada Factor, Ada Grad, etc. So these are the three phases. Let's start with the forwards. I said forward is a mathematical function, right? So let's go ahead and write this mathematical function that takes x as input and use all of these trainable parameters that we marked with matrices and vectors, and then yields the output, the loss, and all the intermediate activations. Instead of having to going back and forth, I'm going to take a picture of this, and I'm going to copy this below, and I will mark on it. Okay, instead of, yeah, not mark maybe, but keep showing it. So let's go. First, forward, say forward. In the first layer, we start with X and we get to H, right? So we know our H11 is nothing but W11 transpose X plus B11. And H12 is W12 transpose X plus B12, and so on and so forth. So we get all of these, and we call this guy our H1. And similarly, since this goes, we can call, let me call this first layer. So therefore, we have H1, which is equal to W1 X plus B1. And we know, let me put it into a box, which is not so difficult, actually. Draw the bottom. and this one such that it is highlighted. I like this little bit of shadowy move. And of course the activation, so I know A11 um, is only obtained from using a sigmoid function or a ReLU function. I'm gonna let's use ReLU, rectified linear unit. So that's pronounced rectified linear unit of H11. So ReLU function, um, ReLU of x is defined like this. The output is x if x is greater than 0 and 0 otherwise. So what it does, it takes as input anything in the real axis, and it gives you x if it is greater than 0, it is linear. If it is less than 0, all you get is 0. It's clipped, right? So it is this is this is rectifying it. And a 2, 2 is again the value of h12, yada, yada, yada. We get this vector, and we call this a1, and therefore we call a1 is equal to, I know we defined ReLU in specifically scalars, but more often than not, uh, it is if it is element-wise operation, we define something for vectors too. So I know this might be bothering for those of you who are like very particular about how the functions are defined. I am one personally, but it is what it is, right? So like for the sake of simplification, we have one output for this activation and this activation, and everything continues similarly. My H2 will take A1 as input, and it is going to be using the W2 as the weight matrix plus B2, and that's my second layer activation, and I get this, right? Why I'm doing all of these, because in the backward I will come and visit all of them. So that's my second layer. And similarly, my A2 is nothing but, again, the value of H2, which is, again, going to be important. I don't want to keep searching for it. So I'm making it just stick to my face, and I understand, oh, yeah, here it was. So these are going to be, amidst all of these difficult things, I know that I will find them. And there's no third layer. The third layer is the classification layer. Classi Right, so we're here, we calculated this, we calculated this, we calculated this, we calculated this, and the classification layer, right? So the classification layer, the last layer. So the classification layer calculates Z logits for each and every one of the classes. Z1 is W3, 1 transpose A2. It takes A2 and B3, 1. And Z2, similarly, W3, 2 transpose A2 plus B3, 2, yada, yada, yada. And therefore, what we get is Z, um, the set of logits is nothing but W3, A2 plus B3. Box it, highlight it. Okay, and from here we get Y, which is softmax of Z. Again, this is a vector, right? And this is a vector. And this softmax, I would like to mention that this softmax function is not one-to-one. That's going to be important in a second when we go to the backwards. What do I mean by one-to-one? Yi is not only coming from x of I. So let's open this up. Let's remember what it was. Yi was exponential z of I, but in the denominator it has everything else, right? So j equals 1 to however many classes, like we call the number of classes k, exponential z of j. And let me mark this also, because this is also important. I will come and then look at my sheet above and then try to find it and use it in the future, right? Uh, so here I would like to pause and talk about it a little bit. Um, this is, as opposed to the ReLU here, this is now one-to-one. It means that if the output for any of the z's here, for any of the z's change, it is going to affect the probability of all of the classes. Similarly, when we go to backward, any change in one of the classes probability is going to affect the logit of other classes, whereas it is not the case in the activation here, but it is a case in the softmax. So that's one important feature that's going to that involves something what we call Jacobian metrics. But I'm not going to bore you with that. I will use in the backward calculation not the Jacobian matrices, but the very calculus that we know and familiar with, and just a little bit of maybe vector calculus, but not Jacobian matrices. I'm not going to startle you so much. And finally, the loss is the cross entropy. I shouldn't write loss, which is L. We defined it L. Cross entropy between Y and R. Again, this is a vector, and this is a vector, right? And it is negative log likelihood, which is calculated negative sum over all classes k equals 1 to capital K rk log yk. So this was my loss. And if you're curious why we're using negative log likelihood, what is this? It means that you missed the previous video. If you want a good understanding of how the cross entropy is being involved, why why there's log and rk is being multiplied here, we already covered it previously. So this is our forward. All right, now moving to the most interesting thing, backward, aka error backpropagation. Why it is called error backpropagation, it is going to be more obvious after I introduce it. So let's say backward. Backward, as we mentioned, up top, backward is the process of calculating the derivatives of every single trainable parameter with respect to the loss. If we would like to minimize the loss, in order to minimize the loss, how much or to which direction I should change my parameters such that it minimizes. So this is, so far we have covered it. And this derivative is going to be instrumental to learn, to update our model. So in theory, let me go ahead and paste my network here so I don't scroll so much. Whoops, didn't work. Paste, paste. Okay, perfect. So this was my network, right? And I would like to say, calculate the derivative of this guy in W1, say W1, right? Or any of this W1 too. So I would like to calculate, for example, dl over the W1. All right, so we know in creating the L, W1 took some act. We know in the forward that L is composed of the Y is composed of by Z. I get Z from A2, and I get A2 from H2, and I get H2 from A1, and I get A1 from H1, and guess what? I get A1 via W1. So W1 affects my node, my loss. But in order to calculate the loss, we use the chain rule. So here, I know my loss is calculated with my WY, and my WY can be calculated with dy dz, and dz dA2, dA2, dH2, the H2, the A1, the A1, DH1, DH1, and finally DW1. Okay, this looks familiar from um, our calculus, right? This is the chain rule. But something is different here. I would like to mention, I would like you to remember what is L. L is a scalar. It's one number. It's one loss number. Despite how big your network is, even if it is taking vectors, images, videos, whatever, there's this one number that you monitor, right? So that's a scalar. Whereas W1, this is a matrix. So DL or DW1, which is going to show me the direction of W1, the resulting, the result of this DL over DW1 has to be a matrix as big as W1. Otherwise, I won't be able to update, right? I want the direction for each and every one of the weights to go such that loss is reduced. So the result of the LDW1 has to be a matrix. Again, let's look at this. So this is a scalar, and I mentioned why this is going to be a vector. So therefore, the resulting thing of this scalar over vector has to be a a vector, right? So dy, like if I had to reduce my, so the answer, the interpretation, English interpretation of this thing is, if I want to reduce my loss a bit, how much should I change the y? To which direction I should change the y? And here, this thing, I'm going to take another color for this, maybe a little bit reddish color, orange, just to warn. Here, now look at this. So this is dy over dz. So if I change my y a little bit, how much my z should change? But wait a second. My y, so this y, every element of this y is created from all of the elements of z. Therefore, this derivative, which is a derivative of vector over vector, but this derivative is a little bit complicated. This has to, let me just so far, let me write, not write what it is yet, because I will go over this. I kind of did cover it in the last video when I was calculating the classification layer. This is a bit involved because yi, so dyi, or a derivative, yi has something to do with all zj, right? So that's it's not one-to-one. It's not element-wise. And again, notice that this is dz over dA2. Like if I change, it is going to flow back. And if I were to calculate this little thing, so dl over dy, so this is my, as I mentioned, this has to be the same shape as y, because it is showing me the direction that the activations should go. So this is my delta y. Notice how I'm writing all of the activations, because the derivative should go through the ones that are in black color. And similarly, look at this thing. So this is the error that's backpropagated to y to reduce the noise, to reduce the loss. And similarly, I get, so this thing, by the chain rule, this is nothing but dl over dz, which is gradient of z, right? And if I calculate this thing, right? So this is nothing but dl over dA2. At some point, we will need that too. And we will have a name for this delta A2. And for all of the activations, all of those that are in black color, this is dl over dH2, which is obtained by dl over dA2, dA2, dH2, right? and there's a name for it and defined as, maybe I should put the triangles on equations, defined as delta H2. So at this point, I would like to pause and write this as, I call this the error term. Notice how the error that exists in the previous layer, the, the layer upstairs, the layer that's closer to the output, is getting multiplied, or yeah, getting multiplied with some derivative term here, as you see, to get you the error that propagates to the layer below that. And that's why this is called error backpropagation. It is going to become more obvious as we continue, as we develop, that in order to go calculate the derivative um, with respect to W1, we want we are not going to start from W1. We're not going to calculate everything. Oh yeah, now I have the W1, and I go to W2, and I go to W3. We're not going to do that. As the name backpropagation suggests, we're going to start from up top and then calculate the derivative dl dw3, and while doing so, I will have to calculate delta y, and then I will have to calculate delta z, and since delta z is the one that's coming to the doors of w2, I will be able to calculate dl dw3 because now I have delta z times dz over dw3 is going to be my dl over dw3. So that's how I will be able to update it. And similarly, I will be able to calculate the a2, and it is going to go backward. That's why our title is backward, right? So we're going to go from up top to here. So to start from the top, I know some part of it we covered in the last video, but now I hope in the grand scheme of things, it is going to be more obvious. It is going to start like it is going to take forever. It looks like it's involved in the layers here. It is going to take some attention here and maybe to come here. And then everything is going to be so simple and fast and repeated as we go backward. So when you get the idea, when the idea is presented, it is similar. So our first goal is to calculate, say, dy, right? So my delta y. Let's start. So first thing, I'm up top. What do I have? dy. So my delta y, which is dl over dy, and which is going to be, again, notice that this is a vector, right? So I have to, when I'm talking about delta y, which is going to be from a scalar to vector, I'm actually talking about this. It's a vector whose elements are something familiar from our college calculus. So I have dl dy1, dl dy2, yada, 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 right? So that's what I'm talking about. And since my y, what was my y? Sorry, my L is equal to negative summation k equals 1 to capital K, rk log yk. So my y, dl dy is going to be, so my dl dy is going to be, or dyi for any of the i's, are going to be, everything is going to disappear because like I'm calculating for any of the y's. In the summation, all of the yi's exist from k equals 1 to capital K, and I'm interested in the ith, right? For the ith perspective, I have this negative here, y r I divided by yi, because the derivative of log of x is 1 over x, right? So that's my ri negative ri dl, negative ri over yi. So at this point, I'm not going to go directly make it into a vector of r over y, because I will have to calculate the next thing. The next thing, since I have, so this little thing will have to change everything else. And this little thing will have to change everything else, you see? And this little thing will have to change everything else. So I have to calculate um, for each and every one of the i's of the probability, its derivative, its how it changes the logit for all of the logits that connect to it. And I know the number of i's and number of j's are the same. So there are the same number of logits that create the probabilities. And what I have to do is I have to calculate the zj of the formula of the yi that includes the zj. So this part is going to look a little bit familiar from the last video. So I know it's going to be exponential z of I, notice how I'm calculating with respect to yi, divided by sum of the, now I'm not going to use j because I don't want it to confuse. I'm going to use some other index because I know this is the summation that I'm calculating for all of them. So the derivative of the upstairs is itself, right? Exponential zi if and only if I equals j. Otherwise, it's 0. So there's a way for me to write mathematically, make it 1 if it is the same, 0 otherwise, and we use the delta function. That, remember the function, delta ij. And let me briefly introduce what this is. Delta ij equal to 1 if I equals j and 0 otherwise. You see how delta ij makes this guy exponential z of I if I equals j and 0 otherwise. And I will multiply with the denominator. And denominator, I don't want to keep typing, keep writing the keep writing the summation symbol. I'm going to call this guy a nice letter, capital S, S for summation, right? Times S minus upstairs numerator itself, exponential z of I, times the derivative of the denominator. Since denominator includes all of the z's, exponential z's, including the j exists, so its derivative is going to be exactly it. The great thing about the exponential functions is that its derivative is the same, divided by s squared. So when we open it up, we have exponential z of I delta of ij times s divided by s squared minus exponential z of I divided by s exponential z of j divided by s. And notice how this one of this s goes. So this is yi times delta ij minus this is yi and this is yj. So I have that. Let me put it in the circled square too, because I'll use it in a second. Okay, let's not get lost. Let's remember where we are. We are about to calculate. Let me add one new page. Okay, we are about to come to here. We're calculating the delta z, the lowercase delta z, this thing. And in order for me to calculate the delta z, I have to multiply the two of them. So I have to calculate delta z, which is something like this, dl over dz1, dl over dz2, yada, yada, yada. I want something like this. So that's my delta z. And my delta z, let's take any of that, right? So dl over dzj, let me keep using the same index for j, is can come from, we learned that dl over dy for all of the i's, and for each and every one of the I, there's a dzj, and I have to count for all of the i's. So far, so good. So like the error that propagates to all of the i's, yi's, will be functional to change the derivative that goes to the zj, right? So let's go ahead and write it in terms. So I have for all of the i's, what is my dl over di? This was nothing but negative ri yi. So negative, let me put the negative ri over yi, and I will multiply it yi delta ij divided by yi yj close parentheses. And let's do some work. If we do some work, if we distribute them, so I have negative over all of the i's, ri, yi's cancel each other, delta ij, and one negative here, another negative comes here, and it becomes plus, and summation all of the i's, I have ri, this yi's cancel each other, yj. Perfect. And I see that when I loop over all of the i's, so this delta ij is going to kill everything except when I is equal to j. So this summation is going to be 0 for all of the i's until the I is equal to j. I will become everything, including j. And when it is j, only then this delta is going to become 1. So to say, it's going to take a photograph of this guy at that very moment. And at that very moment, this ri, which is going to take any value during this counter and summation, but at this value when there's an opening from this delta, this ri is going to be equal to j. It's going to be rj, right? So it's going to be negative rj. And if I were to calculate this, this is a counter over I. So this yi can go outside. So plus this yj. So j has nothing to do with I. This can go outside, and the summation over all of the i's are i's. And guess what? This is 1. And therefore, my dl over dzj is nothing but yj minus rj. This is neat. And which makes my delta z, my nice delta z, the error that comes to the logit is the vector of these. It's a subtraction of two vectors. It is nothing but y minus r. That's a very neat, that's a very great outcome that we see. And if you're thinking, we did all of these work and we're just here, we did not even calculate any update, don't fear. That's one of the most difficult parts of the thing anyway, right? So moving on, we need to calculate the W2, the derivative with respect to W2. So W3, we're already there. So if I were to calculate, let's say let's say I'm interested in calculating delta W31 transpose. What is delta W31 transpose? This is here. Let me mark it with green. So I'm interested in this. And I know part of this was introduced last week because that's the classification layer. But hang on with me because this is going to be, like, if you focus your attention here, it's going to be important. And which is calculated by dl over dw transpose 3,1. Again, I would like to stop and show you that this is a scalar and this is a vector as big as the W31. This is a row vector, and the result has to be a row vector, such that when I get this result, I'll get this delta, and I'll know what my delta was. I'll get my delta W3, and I will know what my W3 was, and I will update it using what I learned here, right? So in order for me to calculate, I know how they relate to the output, right? I know how they should be. I know how the delta z should be calculated, incorporated. So I know delta I over, if I know that delta z is here, and if I can calculate delta z over delta W31. So I just calculated. I know what this is, and I can calculate it from this. So I know W31 is touching only one neuron, which is Z1. Where's my neuron? This is my Z1. So I know my Z1 is calculated via W31 transpose. Its input is A2 plus B31. Therefore, my W3 delta, my delta W31 transpose will be equal to Y sorry, not 2, 3, 1, y1, because it's only touching the z1, right? And I'm calculating this. So this is y1 minus r1 times what is the derivative of this with respect to a2? It is a2 transpose. And similarly, if I were to calculate the derivative of the next thing, W32 transpose, it is now touching the other neuron, Y2 minus R2, which is, again, let's remember, this is delta Z1. This is delta Z2. And its derivative, this thing, is again the same, because Z2 is nothing but W32 transpose A2 plus B32. And it's going to be A2 transpose. And if we were to calculate all of them, I know we mentioned that it was going to be um, just just 3 classes, but we get, so this y1's, y1r1, y2r2, y3r3, it's delta z1, delta z2, delta z3, and all of them, and they create my great vector for delta z. So remember, that's a vector. That's a column vector as big as z, as big as the output of W3, and it's multiplied with A2 transpose. So, so that's, let me delete here, and that gives me delta W3. And here, please notice that what shape am I getting? I am getting, so that's my, whoops, that's my delta Z, as big as Z. Wow, that was a horrible drawing. So that's my delta Z. So that's my delta Z, and that's my A2 transpose. My A2 transpose, I'm writing a column vector, a row vector, right? So that's as big as my input. And notice I'm making my input a row vector, and I'm multiplying, calculating the outer product of my output and the input to it, the output gradient of the output and the input to it. So the way, another lesson that we learned from here is that in the way for us to go, the direction that we should go is composed of the input to a linear layer and the gradient that comes to it, right? And similarly, I could calculate delta B3, which is dl over dz and dz over db3. And you see that db3 is not multiplied with anything here, calculating the z. So therefore, its derivative is always 1. And therefore, my delta b3 becomes dl over dz, which is nothing but delta z. So, so the derivative, so it means that if you want to update the bias, you're going to use the gradient of the activation that comes to it directly. So that's how the bias is calculated. Next, we will move on to move on one layer. So from here, we come here, and we were able to propagate the error all the way to the baby blue ones, meaning the trainable parameters. But now I have to jump to A2. And then such that I know how to update my layers that are not directly touching um, the, the error. So our next goal is to calculate the derivative that comes to A2 such that I can find the derivative that goes to H2, and therefore I am able to find the direction, the steepest descent for W2 and B2. So I know, let's go to our forward function. In order for me to find the derivative that comes to A2, A2 is involved in calculating our Z. So I know how I can go to how I was able to calculate the Z, the derivative that goes to Z. So we will try to find a way to go all the way to z. So what we are interested in, the derivative uh, that's going to a2. So I'm interested in delta a2, and which is defined as dl over dA2. And in order for me to find it, I know through chain rule, um, the activation just above A2 is Z. I know dl over dz. And I know I hit a name for this. I call this delta z. You see how these deltas are changing forms by getting multiplied with different, whatever they get involved. dz over dA2. Okay. Now at this point, let's stop and understand what's going on here. So dz, this is the vector. So I have all of these z's, right? Z1, Z2, Z3, yada, yada, yada. And A2 is also another vector, but this is a long vector. So this is A21, A22, A23. So this is A2. Remember what this was? This was the output activations of the second layer, and this was the logits, right? So I know there's a function that combines the activations to the logits, which is through W3, but now I know this derivative is also a matrix. Why? Because when I'm calculating each and every one of these z's, I need all of these a's outputs through the W3. So I know my any of my output activations, z of I, my logits are obtained through the row vector that creates it, and it takes as input the whole vector of A2. And it takes as input B3 of I. So again, just like this, I have to calculate the derivative of dz dA2, but I know I have to calculate for any of the zi's and A2j's because A2 is a vector and it has several different indices, and zi is a vector, and the derivative between these indices constitute a matrix which we call the Jacobian matrix. But I promised I wasn't gonna go into that, so I'm gonna keep it. So I know, again, let's go ahead and open up this. Let's remove this transpose term, and for the sake of calculating this derivative, let's make it once in the summation formula. So I have j equals 1 to, I don't know how many dimensions. I'm gonna call it d2 dimensionality of the second layer. I have to calculate w3 ij a to j plus b3I. So this, if you notice that this long thing was a description of this inner product here. And so I know for zi, if I were to calculate the derivative with respect to w2j, any of the w2j's, everything disappears, but only one thing remains, and that's w3ij. So that's the derivative for dzi dA2j, right? And if I were to calculate dz dA2, it's a matrix, and this matrix is going to be the transpose of the W3 matrix, right? So therefore, what we have to achieve, so I get it means that the Jacobian, let me go like this, Jacobian matrix is the transpose of W3. So that's what I get. And therefore, to sum everything up, so I'm interested in dl dA2j so that I can calculate all of these A2j's and then get my dl dA2. And I have to calculate, I know dl dzi, and for each and every one of the dzis, I have to calculate dA2j, and I have to sum all of them for over all of the i's, right? Sorry, not D2. I have capital K number of logits because I have k classes, right? And if I sum them up, I have something like I equals 1 to k, w3 ij, yi. So this was yi minus ri. So this is almost like an inner product. I'm going through one index of this vector. I know this vector, W3 vector. I already had that vector. And so then I think you see where I am going with this. So if I were to calculate dl over dA2, which is, again, this is a vector, I have to find something like this, dl over dA21, dl over dA22, yada, 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 and dl over dA2, however many d2 um, indices there are. So it is going to be my dl over dA2 is going to be a vector that's going to be calculated. If I were to have all of them here and make this a vector, I will have nothing but the transpose of this W3 matrix multiplied with whatever comes to it. And I have a definition for it, so that's my delta A2. Let's go ahead and put this into box as well. Here we did some math, but before moving on, let's go ahead and understand what's going on. So in order for me to calculate the error that's being backpropagated through a layer to its input, note that the output of this layer is z, and the input of this layer is a2, and the gradient that comes to it is delta z. In order for me to find the gradient that goes to it, it so happens that you calculate the transpose operation. So it takes k number of input errors, backpropagates it to the input. If I were to introduce it like this, so we know like what I'm talking about is z was w3a2 plus some b, and coming from dz to a2 happens, so delta a2 then becomes w3 transpose delta z, almost like poetic, because this one doesn't get involved because it doesn't have any of the term that's being backpropagated. So since z and a2 are linearly related through w3, dA2 and dz are again the same way related through the transpose of W3. So this last part is quite intuitive, but how it is the case is through all the math that we did here. All right, so the next phase that we need to find the value. So we need to find dA, so we need to find the delta H2, right? And it's d delta H2 is defined as dl dH2, which can be obtained via d L over d A2 dA2 dH. This is simple because this was an element-wise operation. The derivative of every element in the output, which is A2, was only created from the corresponding entry. And I know for any of the i's, so the AI over the A2I, the H2I, before I write this, maybe I should let me rewrite the forward. So AI, A2I is obtained by a ReLU of H2I. Therefore, so ReLU was something like this, right? So it was H2I if H2I is greater than 0, 0 otherwise. So the derivative here, derivative of x, so this is x, derivative of x is 1, derivative of 0 is 0. So therefore, its derivative, so the derivative of this, derivative of ReLU, is should be something like this. So if we call this ReLU, right? So derivative of this has to be something like this, right? So before 0, it's all 0. After 0, it's constant, it's 1. So I'm going to call this a unit step function. I'm going to call it ux. So that's the ReLU, d-ReLU of x over x. So that's the derivative of ReLU. So if I were to calculate dA2i over dH2i for each and every one of the I indices, I will have nothing but u of h2i. If it is zero, if it is greater than zero, it is 1. If it is less than 0, it is -1. So uh, therefore, if I were to write then dA2 over dH in the vectorial form, so this is the vector, I can write it as UH2, right? So U is the unit step. So like you're getting the activation if it is there, if it is greater than 0, or nothing if it is not there. So therefore, the delta H2 is dL over d A2 d A2 over d H2, which is going to be delta H2, the error that I previously calculated. Sorry, delta A2, delta A2 times U of H2. So it basically, if I'm getting the A2, and if I'm not multiplying it with the ReLU, only if I'm eliminating the negative ones, it is almost like getting the value of this thing, right? So if I'm having what comes to me, remember I'm moving backward right now. I have the A2, now I'm going to H2. I'm calculating the delta H2, and the derivative that's selective of the H2 is the unit step. So if I'm taking whatever comes and making everything, making the non-zero one zero, so what I am applying is almost here really, but let's not make it confusing here by introducing another level of complexity. So I'm gonna keep it as such. So that's my derivative that comes that's being backpropagated. So where am I? I came all the way to here. I came to H2. Now, since I'm here, now I'm able to calculate my steps for W2. But guess what? Now this is the point that we will benefit from what we have learned in the layer upstairs. So now I'm interested in step of W2, and step of W2 is going to be nothing but I know that it is the outer product, and it is going to be the outer product between whatever comes to it, and what comes to it is delta H2, and it's multiplied with its input. Its input is A1 transpose. Remember, it is exactly the same that we found for the output layer. Classification layer. And similarly, if I were to calculate delta B2, which is going to be the update for the bias, it is whatever comes to it, right? That's why I am fixating in calculating the errors that come to the activations. And similarly, now I came to here. I backpropagated all the here, and I found, now I'm interested in delta A1, right? It's similar. If I were to calculate delta A1, which is the error that's going to backpropagate to it, I know the error that came to the output of it, which was delta H2, and I know A1 and H2 are related through this W2 matrix, but now I have to multiply with the W transpose of the W2, right? Remember that's something we solved a moment ago. See how everything started so slowly, but now it's picking up because it becomes the same operation. Similarly, if I were to calculate the derivative of H1 from what came to the activation, it is the same thing, delta A1 times the unit step of H1. sorry, h1. That's it. So I was able to calculate the derivative, and these are all, notice that these are all mathematical functions that can be programmed, that can be um, calculated and run via computer programs. And finally, I'm interested in, whoops, I'm at the first layer now. Finally, I'm interested in finding the delta W1, which is the outer product of its output. So delta H1 times its input. Its input is X, right? So that's the last thing that I found. And finally, delta B1 is whatever comes to its output, right? So these are my gradients. Finally, why did I calculate all of these things? Let me get my red pen. 3, update. So I calculated all of these so that I can call stochastic gradient descent or other momentum-esque methods. All right, didn't like my word momentum-esque. All right, SGD says all of my W1 is going to be equal to W1 minus some step size delta W1. B1 equal to B1 minus some step size delta B1 because I calculated it. And W2 equal to W2 delta W2. B2 equals to B2 some step size B2, delta B2. And finally, W3 is equal to W3 minus some step size delta W3, and B3 is equal to B3 negative minus some step size delta B3. This is how training neural networks are done.